Welcome back to Silent Science World, this quiet corner of the night, the place where curious minds come to rest while wandering through the wonders of the cosmos. Tonight we turn our attention to a world that has pulled at human imagination for as long as we have looked up at the sky, a small rust-colored point of light that our ancestors watched with wonder and that our machines now study with patience. Tonight we drift toward Mars. From here on Earth, it looks like a quiet ember burning in the dark, distant and still. But that stillness is an illusion. Beneath its dusty skin lies a story that stretches back further than we can easily imagine. A story of flowing water, shifting skies, and the quiet possibility that something may have once stirred there, or may still be resting, hidden from every eye that has ever searched for it. As we move gently through this journey together, let yourself stop picturing Mars as a barren, forgotten rock. Picture it instead as a place still full of open questions, a planet that may once have looked strangely like our own, and one that may still be holding on to secrets large enough to change how we understand life itself. Before we begin, if these slow, wandering journeys bring you comfort, feel free to leave a like or share a thought in the comments below. It helps this quiet space find its way to more sleepy minds like yours. For now, though, there is nothing you need to do but settle in. Let your shoulders drop, let your breath slow down, and let your mind drift across the surface of another world as we explore, together, the hidden story of life on Mars. Let's begin. There was a Mars before the Mars we know. Long before it became the frozen, wind-scoured desert we see in photographs today, the planet wore a very different face. Its sky was thicker, its volcanoes rumbled with heat, and water, real moving water, carved its way across the surface in rivers, pooled into lakes, and may have gathered into seas wide enough to reach a horizon. That matters more than it might seem, because life, at least the only kind we understand, needs more than water alone. It needs usable chemistry. It needs energy. It needs quiet, stable corners where small reactions can happen again and again until they become something larger than themselves. Early Mars may have offered every one of those ingredients at once: rock, heat, carbon-rich compounds, minerals, liquid water, all gathered together on a young, restless world that was still shaping itself from the inside out. It is a strange thought to sit with. While Earth was slowly becoming a cradle for life, Mars may have been running a quiet experiment of its own. Somewhere in that ancient mud, or buried stone, or warm underground pool, chemistry may have taken its first uncertain step towards something alive. Look at Mars now, and none of this feels possible. The air is thin enough to barely count as air at all. The cold is brutal. The ground is drier than the harshest desert Earth has to offer. And yet, the landscape itself tells a very different story than the one written in today's weather. Spacecraft circling overhead have photographed dry riverbeds, fan-shaped deposits that look exactly like river deltas, smooth rounded stones shaped the way only flowing water can shape them, and minerals that, as far as we know, only form in the presence of water. These are not small or easily dismissed clues. They are the remains of a planet that once behaved in a completely different way. Rain or snow may have fed streams that ran for seasons at a time. Lakes may have lingered long enough for fine sediment to settle in careful layers, one on top of another. There may have been shorelines. There may have been seasons. There may have been water quietly working its way through soil, the way it does here on Earth. None of this means Mars was ever a twin of our planet, but it may once have been close enough to feel, in some strange way, familiar. The most haunting part of all this is that the warmer, wetter Mars did not vanish without a trace. Its memory is still written into the ground, waiting for anyone patient enough to read it. Consider a single ancient basin, one of the most closely studied places on the entire planet. Long ago, water flowed into this crater and spread into a calm, standing lake. At its edge, a river built a delta, laying down mud, sand, and fine minerals in careful, repeated layers. On Earth, deltas are some of the best places to preserve traces of ancient life, because they gather material gently and then bury it quickly, sealing it away from the destructive forces above. This is why that particular Martian basin feels so important to the people who study it. It is not simply a hole in the ground. It is the remnant of an old water system, one that carries a record of changing conditions locked inside its stone. If anything ever lived in that lake, or along its muddy edges, the faintest chemical or structural trace might still be sealed inside those layered sediments. The landscape is silent now, but its rocks may still be holding onto evidence from a time when Mars had open water resting quietly beneath an open sky. Scientists working with samples from ancient Martian rock have found something else worth sitting with: carbon-based molecules, tucked inside stone, that formed when fine sediment settled through calm water long ago. These molecules matter because carbon sits at the center of every form of biology we have ever encountered. They are not, on their own, proof of life, since non-living chemistry can produce similar molecules under the right conditions. Still, finding them there is deeply intriguing. It means delicate carbon chemistry survived, locked inside rock that once belonged to an environment capable of supporting life. Think about what that quietly implies. Mars did not simply have dry dust and rust-colored stone. It had places where water, minerals, and complex chemistry all met at once, and where that meeting was preserved for billions of years. On Earth, those are exactly the kinds of settings where life tends to leave its faintest fingerprints behind. One robotic explorer sent to study this ancient basin drilled into a rock that scientists nicknamed for its unusual patterns. The sample it collected turned out to be one of the most fascinating pieces of Martian material ever gathered. It contains organic compounds, distinctive mineral textures, and small spotted features associated with chemical reactions that, on Earth, can sometimes be tied to microbial activity. That detail matters, but it does not mean life was present. Nature is remarkably skilled at producing patterns that resemble biology without any biology involved, especially in ancient rock shaped slowly by water and chemistry over immense stretches of time. And this is precisely why that sample is so valuable. A rover can study Mars with extraordinary instruments, but a laboratory here on Earth can examine the smallest details with a level of precision no machine on wheels could ever carry across space. If that sealed sample ever makes the long journey home, researchers could test it using tools too large, too delicate, and too complex to ever send to another planet. The wonder here is not that we already know what any of it means. The wonder is that Mars has handed us a question so specific, so strange, and so genuinely worth chasing. If life still exists anywhere on modern Mars, it is almost certainly not living out in the open. The surface today is a hostile place for biology. Radiation reaches the ground far more easily than it does here, protected as we are by a thick atmosphere and a strong magnetic field. The air is thin. Liquid water cannot stay stable for long. Temperatures swing wildly between day and night. But underground, the story might be entirely different. Soil and rock can block much of that radiation. Temperatures beneath the surface may hold far steadier. Ice tucked away from sunlight may remain intact, and pockets of salty moisture might occasionally form in hidden, sheltered spaces. Here on Earth, entire communities of microbes live deep below the surface, far from any daylight, drawing their energy not from the sun, but from chemical reactions between rock and water. That earthly example opens the imagination in a powerful way. If life ever began on Mars, it may not have needed to disappear when the surface turned hostile. It may simply have retreated downward, following the last remaining water into cracks, pores, and buried shelters. The most important living things on Mars, if any exist at all, may have never once seen the sky. The story of Mars is, in many ways, a story of loss. The planet once wore a much thicker atmosphere, one that helped shape a far gentler surface than the one we see today. Over time, most of that air was slowly stripped away into space. Mars is smaller than Earth, with weaker gravity, and at some point in its distant past, it lost its global magnetic shield as well, leaving its upper atmosphere far more exposed to the relentless push of the solar wind. As the air thinned, pressure dropped, water became harder and harder to keep stable, and the planet gradually cooled into the dry, wind-scoured world we know now. This transformation is part of what makes Mars feel so quietly tragic and so endlessly fascinating. It may not have begun as a barren world. It may have slowly become one. A planet that once carried moving water and far richer possibilities was reshaped, piece by forces working on a truly planetary scale. In a real sense, the search for life on Mars is also a search through the ruins of a lost sky. Even now, the red planet holds vast reserves of buried water ice. Mars may look dry from a distance, but it is far from empty of water. Ice lies within its polar caps beneath its surface soil, and scattered across parts of its middle latitudes. Some of it sits close enough to the surface that future explorers may one day be able to reach it directly. That ice is more than a survival resource. It is a scientific treasure in its own right. Frozen water can preserve a record of ancient climate, layer by layer, much the way ice sheets on Earth quietly store centuries of ancient air and dust. It may also help protect delicate organic chemistry from some of the harsher conditions found at the surface. For future explorers, that buried ice could one day become drinking water, breathable oxygen, and rocket fuel. For scientists, it may reveal exactly how Mars changed from a wetter, gentler world into the frozen desert we study today. The same hidden ice that could one day help humans survive there may also help explain whether anything ever survived there before us. A discovery does not need to be large to be revolutionary. It might be nothing more than a microscopic structure locked inside ancient rock, a chemical pattern left behind by long-dead cells, or a mineral texture that, as far as we know, only living communities are capable of producing. The size would not matter at all. The meaning would be enormous. If researchers ever found convincing evidence that life once existed on Mars, it would demonstrate that biology is not some rare one-time miracle confined entirely to Earth. It would mean life appeared on two neighboring worlds within the very same solar system. That single fact would suggest the universe may be far more generous with life than we have ever dared to assume. Even long-extinct microbes would rewrite the story completely. They would transform Mars from a planet defined by geology and weather into a second chapter in the larger history of life itself. A single tiny fossil could become one of the greatest discoveries our species has ever made. Robotic explorers have completely reshaped our understanding of Mars, but human explorers would bring something different to the search. People can choose samples quickly, notice unexpected details a machine might overlook, drill with flexible judgment, and adapt on the spot when a landscape surprises them. The most promising searches may take place below the surface, where ancient materials remain shielded from radiation and the slow grind of weathering. Future explorers might examine buried ice, carefully split open layered rock, or venture into ancient lava tunnels, where time has left things far better protected. This would be anything but casual exploration. It would demand careful suits, sealed tools, strict procedures, and a deep respect for the risk of contamination. The goal would always be to avoid carrying Earth's own life into the very places we hope to study with clear eyes. And yet there is something quietly breathtaking in the possibility. One day, a human hand may lift a piece of Martian stone and hold within it the answer to whether life ever truly began on another world. That ancient basin we spoke of earlier once held a river delta rich with possibility. Seen from orbit, the place looks almost like a frozen memory of moving water. A channel enters the crater, spreads into branching shapes, and leaves behind a fan of sediment strikingly similar to river deltas found here on Earth. That resemblance is a large part of why explorers were sent there in the first place. Deltas are, in a sense, nature's own collectors. They gather mud, minerals, and tiny chemical fragments from across wide stretches of landscape, then quietly bury them in careful layers. On Earth, those layers can preserve delicate traces of the past for immense stretches of time. In this particular Martian basin, each band of rock may represent a shifting shoreline, a changing current, or a season when the river carried fresh material into the lake. The wonder here is not simply that a river once flowed through this place. It is that the river may have delivered ingredients from far beyond the crater itself and tucked them away safely in stone, creating one of the very best places on the entire planet to read Mars's ancient story. Another crater, studied by a different robotic wanderer, preserved ancient lake mud inside the layered rock of a towering central mountain. That mountain rises from the crater floor, almost like a geological library, built from stacked layers of sediment that quietly record changes across an immense span of time. Near its base, researchers found fine mudstone, the kind that forms when tiny particles settle slowly through calm, still water. That detail matters because mud can seal away information with remarkable gentleness. It can capture delicate chemical clues without the violence of a sudden flood or crashing debris. The same rover also found signs that the ancient water there was not wildly acidic or impossibly hostile to life, as we understand it. It may, for a time, have been a fairly mild, even welcoming lake environment. As the rover climbed higher, it moved slowly through the pages of Martian history itself. Lower layers spoke of quiet lakes. Higher layers told the story of a world steadily drying out. One single mountain became a timeline of a planet slowly losing its wetter, younger years. Mars had flowing rivers long before Earth had anything resembling complex animal life. The dry channels scattered across its surface are ancient almost beyond easy imagination, many of them carved billions of years ago, when life on Earth was still mostly microscopic, and the great unfolding drama of forests, animals, and eventually people had not yet begun. This gives Martian rivers a strange kind of quiet power. They were flowing beneath a younger sun, across a world whose future would eventually turn sharply away from habitability. Their ancient channels still cross the surface today, largely because Mars lacks Earth's active weather systems, oceans, and shifting tectonic plates. Here on our planet, old riverbeds are often erased, buried, folded, or slowly recycled by geological processes. On Mars, they remain instead, like abandoned handwriting left on the landscape. Some valleys twist their way across ancient highlands. Others feed directly into basins where lakes may once have formed. To study them is to witness water moving through a world that was once alive with geological activity, at a time when Earth itself was still preparing the stage for anything resembling complex life. Not every channel on Mars tells the story of a slow, steady river. Some landscapes look as though enormous surges of water once tore through them with tremendous, violent force. Wide outflow channels stretch across parts of the surface, far larger than any ordinary stream could ever carve on its own. They suggest sudden, catastrophic floods, possibly unleashed when underground water broke free all at once, or when buried ice was rapidly melted by heat rising from deep below. Picture a sealed reservoir trapped beneath frozen ground for uncounted ages, then suddenly released in a single overwhelming surge. Water would tear through solid rock, carry massive boulders along with it, carve streamlined islands out of the landscape, and race toward the lower plains below. The event itself may have lasted only a short time compared to the vast age of the planet, but its mark would remain etched into the surface for billions of years afterward. These channels reveal that Mars was shaped by more than slow lakes and patient streams. It also experienced sudden, dramatic moments of release when hidden water burst outward all at once and rewrote entire landscapes in a matter of hours. One of the boldest ideas about early Mars suggests that a vast ocean may once have covered much of its northern lowlands. The evidence remains debated among researchers, but it is a genuinely fascinating possibility. Some scientists have traced what may be ancient shoreline features circling the planet, as though water once stood at a common level across an enormous basin. If that interpretation holds true, Mars was not merely a world of scattered ponds and temporary streams. It may have held a body of water so vast that it shaped its climate, weather, and chemistry on a truly planetary scale. The northern plains sit noticeably lower than the southern highlands, forming a natural basin where water would have gathered. Such an ocean would have changed nearly everything. Waves may have worked steadily at its edges. Sediment may have gathered slowly along its floor. Even if that ancient sea was icy, temporary, or uneven across its surface, the sheer possibility gives Mars a lost geography that is almost impossible to ignore. Even today, Mars carries minerals that can only form through long, sustained contact with liquid water. Orbiters and ground rovers alike have identified minerals that are genuinely difficult to explain without water lingering for extended periods. Some of these minerals form when volcanic rock is slowly altered over time. Others appear as deposits left behind when water evaporates away. Together, they act almost like chemical footprints, each one pointing toward a different ancient environment. Certain salts hint at slowly drying basins. Certain hydrated minerals show that water actually became woven into their crystal structure. These discoveries matter deeply because water that lingers, rather than water that merely splashes and disappears, can change rock in far deeper and more revealing ways. By carefully mapping these minerals from orbit, scientists can trace where water once pooled, flowed, soaked into the ground, or slowly vanished altogether. Mars does not need to tell its story in words. Its stones have been altered by contact with water, and that alteration has become a language of its own. Every hydrated mineral is, in a sense, a small confession from the planet's wetter past. Clay minerals, in particular, are some of the most valuable materials in the search for ancient life. They form when water alters rock, often under conditions that can be fairly gentle. Their tiny, layered internal structures can trap and shield delicate molecules that might otherwise break apart entirely. On Earth, clays are remarkably good at preserving traces of past environments because they can hold chemical information safely within microscopic spaces. On Mars, this makes clay-rich regions especially tempting targets for exploration. If carbon-based compounds ever settled into the mud at the bottom of an ancient lake, clay minerals could have helped protect them from later damage. They cannot stop the passage of time completely, but they can slow destruction and improve the odds that something meaningful still remains, waiting to be found. Life does not always require sunlight. Here on Earth, many microbes rely on chemical reactions for their energy instead, and sulfur can play a powerful role in those reactions. Mars carries many sulfur-bearing minerals across its surface, and they point toward a planet with genuinely active chemical environments in its past. In some ancient settings, sulfur compounds may have moved through water, reacted with surrounding rock, and created energy gradients that microbes could theoretically have used. This does not prove that anything was ever alive there, but it does mean the available fuel options were far more varied than simple sunlight at the surface. Sulfur chemistry is especially interesting because it can function in places where light is weak or entirely absent, such as underground water systems. If Mars ever sheltered microbes beneath its surface, they might have relied on chemical exchanges rather than photosynthesis to survive. Iron is more than just a pigment on Mars, even though it gives the planet its famous rusty color. Iron can shift between different chemical forms, gaining or losing electrons along the way. On Earth, certain microbes use exactly those reactions as part of their metabolism. They do not consume iron in any ordinary sense, but they draw energy from the transformations it undergoes. Mars holds abundant iron-rich minerals, and ancient water could have created places where different forms of iron met and reacted with one another. Such zones would have been scientifically exciting for two reasons at once, offering both a record of environmental change and a possible source of usable energy. It is tempting to hear the word organic and immediately picture biology. But in scientific terms, organic simply refers to carbon-based chemistry. Such compounds can come from living organisms, yes, but they can just as easily form through volcanic activity, arrive by meteorite, or emerge from reactions driven by sunlight and radiation. This is precisely why discoveries on Mars must always be handled with patience. Carbon compounds are exciting because life as we know it depends on carbon so deeply, woven into proteins, membranes, genetic material, and countless biological structures. Yet carbon can just as easily exist in lifeless dust, ancient meteorites, and chemical mixtures that never once became alive. The real challenge is context. Researchers must ask where the compounds were found, what minerals surrounded them, how old the surrounding rock actually is, and whether the overall pattern matches known biological processes. Mars keeps offering pieces of a much larger puzzle. The hard part is knowing whether those pieces belong to life, to simple chemistry, or to some combination of both. The early solar system was a chaotic place, full of constant impacts. Asteroids and comets struck young planets, carrying ice, metal, and carbon-rich material along with them. Mars would certainly have received some of that cosmic delivery. These impacts could have brought organic ingredients in from space and mixed them directly into surface rock, ancient lakes, and underground hot water systems. This matters because a planet does not need to manufacture every ingredient on its own. Material can arrive from far beyond its surface. Meteorites falling into ancient Martian water may have enriched the local chemistry in ways the planet alone never could. Mars and Earth have not been isolated from one another throughout their long history. When a large asteroid struck either planet, the impact could blast fragments of rock directly into space. Some of those fragments traveled for millions of years before eventually falling onto the other world. This means pieces of Mars have genuinely reached Earth, and it is entirely possible that pieces of Earth have reached Mars in return. Powerful impacts can launch material fast enough to escape a planet's gravity altogether, and some of those traveling rocks may remain relatively protected deep inside during their long journey through space. This has led to genuinely deep questions. Could hardy microbes ever survive such a journey, sealed inside stone? Could chemistry, or even life itself, have moved quietly between neighboring worlds? No one currently knows whether biology ever traveled this way, but the possibility changes the entire framing of the story. Mars and Earth were never truly separate experiments. They were two worlds sitting within throwing distance of one another. Some rocks found here on Earth carry a chemical fingerprint that clearly matches Mars. Scientists know this because gases trapped inside certain meteorites closely resemble the Martian atmosphere as measured by orbiting spacecraft. These stones were blasted off the surface of Mars by ancient impacts, wandered silently through interplanetary space for ages, and eventually entered Earth's sky as streaks of falling fire. Holding one in your hand is almost unbelievable. It is not a sample carefully collected by a mission. It is a natural messenger from another planet entirely. One such meteorite, discovered decades ago, sparked one of the greatest scientific debates of its time. It contained tiny structures, carbonate minerals, and chemical features that some researchers argued might be linked to ancient microbial life. The announcement captured global attention because it suggested Mars may once have been inhabited. Later studies challenged that interpretation, and many scientists eventually concluded that the features could be explained without invoking biology at all. Still, the debate itself was enormously important. It showed just how difficult the search for life can be when evidence is tiny, ancient, and open to several competing explanations. It also sharpened the standards required for any future claim. An idea this extraordinary needs multiple independent lines of evidence, all fitting cleanly together, before it can be taken seriously. Early Earth was not always a gentle cradle. It endured heavy impacts, widespread volcanic activity, and dramatic upheaval as its surface slowly settled into long-term stability. Mars, being smaller, may have cooled much faster. That means it might have developed solid crust, surface water, and genuinely habitable conditions very early in the history of our solar system. This possibility is startling to sit with. For a window of time, Mars may actually have been a better place for life to begin than Earth was. Its lakes, its internal heat, and its chemical diversity could have taken shape while our own planet was still recovering from a violent, chaotic youth. If life truly can emerge quickly whenever conditions allow it, then Mars may have had a genuine head start. The question becomes almost haunting to consider. Did biology begin there first? Did it fail, retreat, or simply leave behind no trace we have yet learned to recognize? Early Mars may not be some minor footnote in the story of life. It may be part of life's opening chapter. A habitable world is not always a calm one. In fact, early Mars was dynamic in ways that could have created many different environments all at once. Volcanoes released heat and gas into the sky. Impacts shattered the crust and carved out new basins. Lakes gathered sediment along their shores. Groundwater may have moved quietly through cracks beneath the surface. And climate shifted over time, sometimes allowing water to flow freely, before forcing it back into ice or vapor once again. This variety matters, because life does not need an entire planet to be comfortable everywhere at once. It needs niches, small pockets of possibility, a warm spring near volcanic rock, a lakebed protected by soft sheltering mud, a fractured underground system rich with chemical energy. Early Mars may have offered a whole patchwork of such places. Some would have been harsh beyond survival. Others may have been briefly, quietly generous. The planet's complexity is exactly what makes it so fascinating. Its habitability was never one simple, uniform condition. It was a shifting mosaic of small chances scattered across a changing world. Ancient Mars received noticeably less sunlight than Earth does, which made keeping water liquid a genuine challenge. Volcanic eruptions may have helped by releasing gases into the atmosphere, including carbon dioxide, water vapor, and sulfur compounds, all of which can influence climate in meaningful ways. In certain combinations, these gases may have trapped enough heat to allow rivers and lakes to form, even beneath a fainter, younger sun. That warming likely was not constant. Mars may have moved through repeating episodes, with volcanic activity thickening the air and briefly altering the chemistry, followed by colder stretches when conditions grew harsher again. That start and stop pattern fits a world where water appears in many places without requiring a permanently warm climate throughout its entire history. Volcanoes were not only builders of mountains on this ancient world. They may have functioned as climate engines, breathing gas into the sky and giving surface water temporary windows in which to flow freely. Even after the Martian surface turned cold, the interior of the planet likely still held on to warmth. Heat from radioactive decay, leftover energy from the planet's formation, and volcanic activity could all have kept deep rock warm long after the surface froze over. If ice or groundwater existed underground, that lingering heat might have kept some of it liquid, tucked away in protected pockets far below. This matters because surface conditions can turn hostile while subsurface habitats remain entirely possible. On Earth, microbes live comfortably in deep rock fractures, where sunlight never reaches and temperatures stay remarkably stable for long stretches of time. Mars may have offered similar refuges, shielded from radiation, buffered against extreme swings in temperature, and connected to minerals capable of supplying chemical energy. Some of the most compelling ideas about the origin of life on Earth involve water heated by rock deep underground. These hydrothermal environments provide warmth, minerals, chemical gradients, and small protected spaces where reactions can repeat again and again. Mars experienced volcanism, impacts, and flowing water, so it may well have produced similar systems of its own. Impact craters could have heated buried ice. Volcanic regions could have driven warm fluids through fractured crust. In those settings, minerals may have acted like tiny natural laboratories, helping simple molecules interact in increasingly structured ways. This is not a claim that life definitely began there, but it shows exactly why these environments remain so exciting to study. They combine several essential ingredients in a single place at once: flowing energy, circulating water, and rock offering both surfaces and raw materials. If biology ever did emerge on Mars, hydrothermal settings would be among the most reasonable places to imagine its beginning. Beneath the surface, fractures in Martian stone may once have formed a hidden world of narrow passages, damp minerals, and quiet chemical exchange. Water moving through these cracks could have carried dissolved elements from one layer of rock to another, creating tiny gradients that microbes might have used for energy. On Earth, deep rock life can survive in places with absolutely no sunlight at all. It grows slowly, clings to mineral surfaces, and depends entirely on reactions between water and stone. Mars may have offered something similar during its wetter eras, when impacts, a cooling crust, and volcanic stress all could have opened pathways deep underground. Even a small amount of depth can change everything on a planet this harsh. Dust and soil can act almost like a blanket against damaging radiation, especially when buried beneath rock or ice. For any ancient organisms, that cover may have mattered a great deal as the planet slowly lost its atmospheric protection. Microbes, if they ever existed there, would not have needed dramatic shelter. A thin layer of sediment, a buried bed of clay, or a shaded pocket beneath loose rubble could have made survival meaningfully more possible. Over time, Mars has been bathed in radiation that Earth's atmosphere and magnetic field would normally soften considerably. That makes the exposed surface a genuinely difficult place for fragile chemical clues to last. Organic molecules can be slowly damaged as energetic particles strike the ground, breaking chemical bonds and altering structures that scientists might otherwise be able to recognize. This is one reason the search for ancient life cannot rely only on what sits in plain sight. A rock exposed at the surface for millions of years may have had its most delicate evidence quietly altered or erased entirely. Sediment can behave almost like a time capsule. When mud, sand, or fine mineral grains settle through water, they can trap fragments of ancient chemistry between their layers. If those layers are later buried, they may be protected from wind, sunlight, radiation, and later surface reactions. This is why ancient lake beds and deltas matter so much to researchers. They do not simply show that water was once present. They can preserve an actual record of what that water carried with it. A newer generation of exploration rovers has been designed with a different ambition than earlier missions, aiming to drill far deeper underground than anything attempted before. Most previous missions studied only the surface or barely scratched beneath it. These deeper drills are meant to reach samples far less damaged by radiation and surface chemistry, preserving a cleaner record of ancient conditions. The exciting part is not simply that such a machine can drill. It is that it can choose exactly where the subsurface may have protected the very faintest of clues. Sometimes, it seems, Mars requires us to dig before it will speak. The dust covering Mars is not merely dry powder. It contains reactive salts that complicate nearly every dream of living there comfortably. For biology, These compounds can interfere with cells and damage organic molecules under certain conditions. For future explorers, they could create real health concerns if dust is tracked into living spaces or clings stubbornly to suits and equipment. Yet these same salts are not purely obstacles. Some microbes on Earth can tolerate related chemistry, and these particular salts can lower the freezing point of water, raising fascinating questions about brief, salty moisture appearing in Martian soil. Life on Earth has a remarkable habit of surviving in places that look completely unreasonable at first glance. Certain microbes thrive in briny pools, salt flats, acidic waters, and icy environments where most other organisms would fail almost immediately. Some endure extreme salt levels by carefully balancing their internal chemistry, repairing damage as it occurs, or slowing their metabolism dramatically. None of this proves Mars ever hosted life, but it widens our imagination of what life is genuinely capable of handling. If Martian environments once contained salty water, they may not have been automatically impossible for biology after all. Stable liquid water is extremely difficult to maintain at the Martian surface today. Chemistry may still create fleeting exceptions. Certain salts can pull moisture from the thin air, or allow ice to melt at unusually low temperatures. Under the right local conditions, tiny salty droplets or thin films of moisture might form for brief periods before vanishing again. They would be cold, harsh, and chemically demanding environments, but their possibility matters because liquid water sits at the very center of habitability. Ice can hold memory the way few other materials can. On Earth, polar ice traps dust, gases, volcanic ash, and chemical traces from ancient climates, preserving them in careful layers. Mars may hold its own frozen records, locked inside polar caps, buried sheets, and icy layers hidden beneath the surface. These deposits could reveal how the planet's atmosphere changed over time, how dust storms rose and faded, and how water moved between air, ground, and ice across the ages. Ice can also protect certain materials from immediate destruction, especially when covered by soil or sediment, which makes it genuinely intriguing for anyone studying the possibility of ancient life. At the poles, Mars stores time in stacked bands of ice and dust. These layers build up and slowly erode as the planets tilt, orbit, and seasons shift across long cycles. Unlike Earth, Mars wobbles more dramatically over time, which can move ice from the poles toward the middle latitudes and back again. The polar deposits therefore become a genuine climate archive. Brighter layers may reflect cleaner ice, while darker bands may carry more dust, together recording changing winds, temperatures, and atmospheric behavior across enormous stretches of time. The most useful water for future explorers may not sit at the poles at all. Some buried ice appears to lie in the middle latitudes, closer to places where human missions might realistically land. That matters enormously, because water is heavy, and carrying every drop from Earth would be extraordinarily costly. If astronauts could access local ice directly, they could turn it into drinking water, breathable oxygen, and the raw ingredients for rocket fuel. This single possibility could shift the entire dream of Mars exploration from simply visiting the planet to genuinely staying there. Dust storms remain one of the great defining powers of Mars. Fine particles can rise into the thin atmosphere and stay suspended there, tinting the sky and changing how sunlight reaches the ground below. Some storms remain small and local, others grow into sprawling regional events, and in rare cases, they expand until nearly the entire planet disappears beneath a dusty veil. For solar-powered missions, this can become genuinely dangerous, since far less sunlight reaches their panels during such events. One beloved robotic explorer, built for a mission expected to last only a few months, ended up traveling and working for years, becoming one of the most cherished machines ever sent to another world. It explored crater rims, studied rocks shaped by ancient water, and crossed landscapes no human eye had ever seen from ground level. Then a massive dust storm darkened the sky above it. Because the rover depended entirely on solar power, the fading sunlight became a serious threat. Its batteries slowly drained, and contact was eventually lost for good. The ending felt almost personal to the people who had followed its long journey, because that little rover had become a quiet symbol of endurance. Its silence also revealed just how deeply Martian weather can shape the fate of exploration itself. Earth is wrapped in a magnetic field generated by motion deep within its metallic core. This invisible shield helps deflect charged particles streaming from the sun and protects the upper atmosphere from being stripped away. Mars once had magnetism of its own, but it no longer carries a strong global field. Instead, scattered patches of ancient crust still hold faint magnetic traces, like fragments of a shield that vanished long ago. This loss changed the planet's entire future. Without broad magnetic protection, its atmosphere became far more vulnerable to erosion by the solar wind, and radiation became a much bigger issue at the surface. The sun does not only shine, it also releases a constant stream of charged particles flowing outward through the solar system. When that stream reaches a planet with little magnetic protection, it can interact with the upper atmosphere and slowly carry particles away into space. Over immense stretches of time, this process contributed heavily to Mars losing much of its air. The effect was never a single sudden catastrophe. It was a slow, steady leak driven by simple physics and repeated endlessly across billions of years. One orbiting spacecraft has spent years watching Mars's upper atmosphere with a very specific purpose, aiming to understand exactly how gases escape and how the sun influences that ongoing loss. By carefully measuring particles, magnetic conditions, and atmospheric behavior, it helps connect the planet's present state to its ancient transformation. This is powerful, because Mars is still losing material today, even if the process moves far more slowly now than during the dramatic changes of its early history. Methane in the Martian atmosphere remains one of the planet's most genuinely puzzling clues. Ground-based instruments have detected occasional rises in methane near the surface, followed by declines that are difficult to explain fully. On Earth, much of our methane comes from living organisms, though it can also form through purely geological processes. That double possibility makes the signal both fascinating and frustrating at the same time. Methane should not persist forever in the Martian atmosphere, since sunlight and chemistry slowly break it down. If it is genuinely present, something may be releasing it relatively recently, perhaps escaping from underground pockets, perhaps forming as rock reacts with water, or perhaps tied to seasonal processes we simply do not yet understand. No mission has yet confirmed living organisms anywhere on Mars. After decades of orbiters, landers, and rovers, the careful, honest answer remains that life has not been found. That does not make the planet any less interesting. In some ways, it makes the search even sharper. Each mission has narrowed the possibilities, revealed ancient habitable settings, and exposed the planet's genuine chemical complexity. Researchers have found landscapes clearly shaped by water, buried ice, organic molecules, and minerals formed in watery environments. But none of these discoveries alone proves the existence of living cells. Confirmation would require evidence strong enough that every other explanation quietly falls away. Bringing carefully chosen rocks from Mars back to Earth would be one of the most ambitious scientific achievements ever attempted. It would connect robotic exploration, orbital capture, careful contamination control, and laboratory science into one long, precise chain. The reward could be enormous. Samples chosen from ancient lakebeds, deltas, or chemically altered rock might contain records that no rover could ever fully decode on its own. Astrobiology would move from remote measurement to direct, hands-on investigation. Researchers could test whether possible biosignatures are genuinely real, whether organic molecules carry meaningful patterns, and whether Mars once preserved habitable environments in far greater detail than we currently understand. One patient rover has already begun this process, drilling into carefully chosen rocks, placing slender cores into sealed, sterile tubes and storing them safely for possible return to Earth. Each tube is almost like a message prepared for scientists who may not open it for years to come. The samples come from locations selected because they record different chapters of that ancient basin's long history, some representing lake sediments, others capturing volcanic rock, altered minerals, or material once carried by ancient water. When humans eventually send both machines and people to Mars, they must also worry carefully about what travels along with them. Earth's microbes can be remarkably stubborn, some capable of surviving dryness, cold, cleaning procedures, and long periods of storage. If they hitchhiked aboard a spacecraft and later appeared inside a sample or a habitat, they could create serious scientific confusion. A discovery that looked genuinely Martian might actually turn out to be nothing more than contamination carried from home. Strict cleaning procedures, controlled assembly environments, and careful biological monitoring all exist to prevent exactly this outcome. The goal is not only to protect Mars from Earth, It is to protect the truth itself. Living on Mars for any extended period would require far more than simple walls and oxygen tanks. A long-term habitat would need systems capable of recycling air, water, nutrients, and waste with extraordinary efficiency. On Earth, nature performs these cycles across oceans, forests, soil, and the atmosphere all at once. On Mars, explorers would need to build small, carefully engineered versions of those same cycles inside sealed spaces. Carbon dioxide would be removed or reused. Water would be recovered from breath, hygiene, and waste. Food scraps could become nutrients. Microbes might help process raw materials, while plants or algae could contribute both oxygen and food, though always under careful control. Growing food there would be equally complex. Plants would need controlled pressure, reliable warmth, clean water, balanced nutrients, filtered light, and protection from radiation. Engineers would need to design the chambers, pumps, sensors, and recycling systems required to keep it all running. A greenhouse on Mars would be more than simply a place to grow crops. It could become part of an entire survival system, using local sunlight, abundant carbon dioxide, and carefully recycled water to slowly turn raw Martian conditions into something genuinely useful for human life. Turning Mars into a second Earth remains one of the grandest ideas in science fiction, but the real planet is remarkably stubborn. It has too little atmosphere, too little easily accessible warming power, no strong global magnetic shield, and enormous environmental challenges standing in the way. To truly transform it, humans would need to thicken the air, raise temperatures, stabilize liquid water, manage radiation, and create conditions capable of lasting for generations. Current technology simply cannot achieve any of this on a planetary scale. Mars has only about a third of Earth's gravity, and that single fact changes what the planet can hold on to. A stronger world grips its gases tightly. A smaller one lets them slowly escape over immense stretches of geological time. If living systems ever do flourish on Mars, they will likely begin not in open valleys beneath a natural sky, but inside carefully sealed structures built entirely by human hands. A habitat could hold pressure, warmth, water, breathable air, and protection from radiation all at once. Within it, microbes, plants, and people might slowly form a managed web of survival. This would not be Mars becoming Earth. It would be Earth's own life quietly building tiny islands of habitability on another world entirely. A day on Mars runs just a little longer than a day here on Earth, a small but genuinely friendly detail among all the planet's harshness. It means sleep, work, lighting, and daily routines could follow a rhythm that feels surprisingly familiar to a human body. Mars also carries two small, irregular moons racing across its sky, far smaller and stranger than our own. One moves quickly overhead, crossing the sky in only a matter of hours, while the other drifts more slowly and appears smaller and more distant. Neither can produce anything like a bright, moonlit night the way Earth's moon does, but together they bring motion, occasional eclipses, and a quiet sense of mystery to the Martian sky. The closer of these two moons is slowly spiraling inward, drawn by tidal forces, and millions of years from now, it may eventually cross a threshold where the planet's gravity begins to tear it apart entirely. Instead of a moon, Mars may one day wear a temporary ring built from its own shattered fragments. It reveals, in its own quiet way, that even the Martian sky is still slowly changing. On Earth, sunsets often glow warm red and orange, because our atmosphere scatters blue light away from the sun's direct path. Mars, with its much thinner atmosphere but abundant fine dust, produces the opposite effect. During the day, its sky can appear butterscotch or faintly pink as dust scatters reddish light through the air. Near sunset, as light travels through more of that dusty atmosphere, the region close to the sun can take on a delicate, almost otherworldly bluish glow. It is a small, quiet lesson in just how differently light can behave on another world. Mars earns its famous color from iron minerals scattered through its dust and rock. When iron reacts with oxygen, it forms oxides, broadly similar in idea to rust here on Earth. These minerals spread across the surface as fine dust, tinting the entire planet in shades of red, orange, and brown, a color that has shaped human imagination for thousands of years, long before we understood the simple geology behind it. Even without a strong global magnetic field, Mars can still produce auroras of its own, guided instead by scattered patches of ancient magnetism preserved deep in its crust, combined with interactions between its atmosphere and particles streaming from the sun. Some of these auroras glow,